Hey guys, so I just want to put a video together for what we talked about today in terms of data analysis for simple harmonic motion. We were doing part 3. I think this was supposed to be part A. Sorry about that. This is where we were graphing. Maybe it is part B. I think it is part B. If it is part A, sorry, but I think it's part B. We were trying to figure out the relationship between mass and period, and then the second part of part B is figuring out the relationship between mass and velocity, and that's what you're doing for homework later. Okay, so when you're getting this data from your different trials, the amplitude was held constant, right? So we were looking at the relationship between mass and period. So just from looking at our data in our data table, we can see that as the mass increases, your period should be increasing and changing. And since period and frequency are opposite of each other, right, or inverse of each other, as the mass increases, technically your frequency decreases. So the way we can read that is as your mass increases, it takes longer for a cycle to happen, right? And then if your mass increases, it decreases the number of cycles that happen per second. So that's why your frequency decreases. And we know that because we looked at we found the definitions of period and frequency. Okay, so in order now, when you're looking at this data, it's really easy with our eyes to try to find linear relationships, but we can't just assume things are linear, so we need to graph our data. And that's what we were doing here. We were graphing period on the y-axis versus mass on the x-axis. And you were asked to fit with a linear line of best fit and fit with another line of best fit and try to deduce your way to what this relationship should be. And here, right, we might not know right off the bat what relationship we're going to have, but we should be able to use physics to deduce ourselves to a reasonable answer, right? It might not be the right answer, but it should at least be reasonable, okay? So we have 5 data points, and 5 data points is a little hard to see the trend. We'd probably want to see 10 or 15 with large variances in mass so that we can really see what's happening. But our springs, and we were limited in how much mass our springs could have and all of that. So we have the 5 points that we have, and we saw something that kind of looked like this, which could, right, you might have a linear fit, you might have a quadratic fit, which would look like this, right, which both have pretty high correlations, but let's talk about the physics of what's happening. So if the amplitude is held constant and the spring is held constant, let's think about if we have the constant spring and we have a constant amplitude, right, the distance that the spring is stretched, if both of these things are held constant, then that means that the force throughout all of these trials was the same, right? This must be the same between trials. And if the force is the same, let's go to Newton's second law, right? If the force is constant between trials, right, that means that as our mass increases, our acceleration must change accordingly to keep the force constant. So we were increasing our mass, so we should have seen a decrease in acceleration, so your velocity was less, and therefore your period changed, right? So that's why we see a relationship between period and the mass, okay? So over time, right, as I keep increasing the mass, I should keep seeing a decrease in acceleration. If we were to extrapolate, right, and now here's where our physics understanding comes into play, right? At no point every time I increase the mass, no matter how much I increase it by, I will keep decreasing the acceleration. There is no time in which I add more mass and the acceleration starts to increase and the object starts to move faster. So if I were to extrapolate, if we fit with a quadratic, right, there would be some turnaround point if we extrapolate. And this implies that if we increase the mass, at some point the acceleration also increases, which we said doesn't make sense because the force is staying constant and the relationship between mass and acceleration is a indirect proportionality, right? As one thing increases, the other thing must always decrease. So a quadratic relationship is not a good relationship for this to be. Even though the line fits right, right, and has a high correlation, the physics of the extrapolation does not make sense. Linear, on the other hand, right, we see that as mass increases, the acceleration decreases in the time it takes. Now, the thing that we need to look at when we're dealing with linear is, are all increases of mass the same, right? Do they all produce the same change in the variables we're seeing? Because when I go from here, right, from, let's call this 100 grams to 200 grams, right, I see the same increase as if I go from 1,000 grams to 1,100 grams, right? That's what a linear relationship means, is the same increase in mass will yield the same increase in our period, okay? Now, if we think back on the F equals ma, right, 100 to 200 kilograms is a doubling of the mass. So what I should see is a halving of the acceleration. So I should see a doubling of the time it takes. If I were to look at 1,000 to 1,100 kilogram mass, right, that is not a doubling, right? So I don't see a halving of the acceleration. It does not yield the same effect on the time based on the relationships in physics that we know. I am agreeing that we are increasing the mass, but we're increasing it by 10% or 1/10. Oops, that says 100. So I'm seeing an increase in mass of 1/10. So I should see a decreasing in the acceleration, I did it again, of 1/10, right? Which is not the same thing as a 200, or of a doubling and halving, okay? So while I do see the relationship of as one increases, the acceleration decreases, or as mass increases, period increases, it's not the same effect all the way through, okay? So linear, right, this is our linear fit, is also not a good physical, right, through physics, does not fit with what we're seeing, okay, or and with the theory. So what we do know is our period and our mass are seeing some changes where it dampens over time. The effect of your mass change starts to impact the period smaller, right? So we get a big change as we're doubling and tripling and quadding, right? But then as we go, our change is affecting our period less and less because the mass change is affecting the acceleration less and less. So if linear fits and quadratic fits don't work, our next best thing is to try a power series fit. Okay, a power series fit is basically taking x and raising it to some value, right? Some constant value. And, you know, it could be 2, it could be 1, right? If it's 1, then that means it's pretty linear. So power series gives us a little bit of flexibility to see the relationship between the variables, and it also allows us to see non-traditional relationships. So I'd say linear is a pretty traditional relationship. If I put a linear line on here, I'm forcing the data to be linear. If I try it through a power series and I get a factor of 1, it's like raising x to the 1, which is just a linear fit. So I'm letting the data do the talking. Same thing with quadratic. I could put it in, and if I get x squared, like maybe that is a quadratic fit, as opposed to forcing it to be quadratic. So here, right, y is equal to some, I forget the variables that they use, but it's like axc. When you fit your data, you're going to see that y is equal to some value x raised to some number that is really close to 0.5. I saw some 0.49s, I saw some 0.504s, right? Those are all, if we're trying to find a relationship, take into account your uncertainty and errors in your lab. A 0.49 and a 0.48, right? Those could be thought of as a 0.5, right, with an error. And now if you get something that's like 0.2, that is too far away to say error has gotten us there, so then we would have to try something else. But if you get this fit, it's the same thing, right? Y is equal to x raised to the 1/2, which is also known as the square root of x, right? So we see this relationship of y, I'm going to say is proportional to, because I left the constants out. Okay, so in this case, y is our period, and we're going to say y is proportional to the square root of the mass. As we are looking at this relationship, the period is related by a function of the square root of the mass. And there's our A value tells us something different. We can talk about that a little bit, like what would that be in terms of our lab. But for right now, the important part is to realize that the relationship we have based on our data and based on talking about the physics is a square root relationship.